So what we see here is a WebGPU version of the points demo that I demonstrated in the last video for OpenGL. First thing you'll notice that's different is that the point size is fixed here to the single point, because that's how this works. If we wanted to do something similar, we'd have to instance a quad or something along those lines, and I have a demo that will do this at a later date, so I'll be demonstrating that. And again, with this, we can see that we can again give it more points to render, and you can see it's very efficiently rendering those. And in fact, we can get silly with this. We can, 100 million points. It's going to be relatively slow, just because it takes time to generate the buffer. And as you can see, we're not getting that 30 frames a second, but it will still handle this sort of large amount of data quite well. We do eventually overflow buffer sizes, and WebGPU has limited buffer size. If you really do need to go to much larger data sizes and things like that, then your real recourse is most probably Vulkan, because that seems to be able to handle all sorts of much bigger buffers. And as you can see, our slow point at the moment is actually generating this data quickly enough. So it's taking a while. You can see we're doing our initialize. Eventually it will try and render. I think this is going to be quite a slow one though. So this is using the NumPy buffer widget. It's exactly the same as before. Basically, this will render as a queue image to the widget our NumPy buffer that's generated every frame from running our render pipeline. And we also have a shader there which is going to be loaded in. First thing, we're using NGL. We're using NGL in this case just for some of the math types, so Mat3, Vec3, Lookout and Perspective. So we're not importing any of the OpenGL type elements that are needed. This is all purely based on the Mat3, Mat4s, which eventually will get converted into NumPy types to be passed to WebGPU. More of that in a while. And when we get started here, we'll have our basic attributes that we're setting up here. So we've got window width and height. We've also got texture size. The texture size is the size of the texture buffer that we're going to render into. We're creating our lookout matrix as we did previously. As mentioned in the lecture slides, you'll see that there is a difference between the way the screen works in 3D from perspective projection in OpenGL, and this matrix here is a simple matrix which will allow us to convert our perspective projection from GL format, which the perspective function uses, to WebGPU format. So you can see here projection is GL to web multiplied by perspective there, so we just scale it through. So first thing we're going to do is initialize our WebGPU. This is going to do the standard sort of creation of our devices and everything else. So get our default device. We're then going to initialize our buffers, create our render pipeline, and start a timer. And in the previous example, we did similar. Now in this case, I'm creating an empty buffer. This is based on the number of the points, and there's 6 components, because again I'm going to be storing a buffer of contiguous data with RGBA data followed by XYZ data followed by RGB data, and I'm going to allocate an empty buffer first, and then we can use slicing with NumPy. So I'm saying vertex data is the first 3 columns, so 0 to 3, and that's going to be set with MP random uniform 40 size, number of points there, and then I'm going to populate the next lot with our color data. I'm then creating this buffer on the GPU ready to be used for our rendering. The render pipeline is slightly different than the previous example. So in this case, in our previous example, we were using hard-coded shaders. In this case, I've got my point shader here. If you look at this shader, it's slightly different now. The first thing we're going to introduce is we've got some bindings in here. So bindings are places within the shader that we want to access information from. And in this case, we have a binding for a uniform, and this is the MVP, the model view project matrix that I want to set each frame to multiply all my vertices by. My input is a very simple structure as we had previously. Location 0 is position, location 1 is color. I have my output from the stage, the vertex shader stage, which is going to be position and frag color, and then my vertex shader. And what you'll notice now is I can actually call my shader just vertex main. We still have the @vertex decorator there to indicate that this is a vertex shader, because there's certain things that must be set within that, but we can call this anything. So vertex main is for the vertex shader. All we're doing in this case again is we're multiplying the uniforms.mvp by the input position. So we're doing our transformation, our homogeneous coordinates as we go through, and then I have my fragment shader here, and again I'm going through and I'm outputting the color for the fragment from the input that's passed in here. I'm just going to kill this because it is slowing down my performance, and that's better. So yeah, I definitely went too long on that, and I was just noticing that things weren't working well. There we go, much simpler now. So that's the shader, and to load the shader is actually relatively simple. I'm just opening it, Python context manager there, reading it, and then that code is being passed to my device create shader module, and then that creates a shader module. Then the only difference now in the pipeline is previously we were having individual shader modules for each one, and we were calling main. Now I just specify vertex main. My array stride, again 6x4, I'm just using there are 6 vertices, and I'm assuming that NP float is 4 bytes. Again, I have my input, so float 32 by 3. 0 is shader location 0. The next one, offset is 12, and the shader location is 1. So this is just sort of specifying our generic vertex attributes as it would be in OpenGL. And my fragment, again, fragment main is my main. The only thing now is the primitive topology is now set up to be point list in this case, because I'm rendering points. Again, I could quite easily go back and say something like line list, and we can render that as a series of lines, as you can see there, as I did in the OpenGL one, or I could say triangle list, and I can change it, and then I've got a series of triangles. Notice at the moment there's no depth buffering going on, so that's why it looks odd. In one of the examples coming up soon, I'll be talking about how to enable depth buffering and get that set up. That's an extra complication at the moment, which I'm not going to put in this code, but it is in future demos as we go through and build on this. Now I need to create a buffer for my uniform data. These buffers are typically set up to be on boundaries of specific size, and each buffer I think is a maximum of 256 bytes. So in this case I'm creating one with 16 bytes in it, which it fits nicely on a boundary for everything. I'm using a named data type here, so dtype MVP is a float 32 by 16. It means later on I can set this by using NumPy's dictionary values. It just makes it easier to write the code to make it read better. In this case, I'm calling 2 bytes on uniform data to convert it into raw bytes. The buffer usage in this case is uniform, and this is going to be copied to destination. And the other thing is, you'll notice now that we've got these labels. At every stage of the pipeline, we can begin to add labels into our code. This is really useful when things go wrong because we can name things, and these will generally get printed out in debug information when it all goes wrong. And it will go wrong because this is quite a complex API. Next, we need to bind this information to our pipeline, and this is what bind groups are for. So I'm going to create a bind group layout, and then within this we are going to say what resource is bound to this buffer and what binding in the shader this matches. Later on we'll see that we may have to generate multiple buffers for multiple different things. So the process is quite complex, but in modern OpenGL you can just say set uniform draw, set uniform draw, set uniform draw. You can't do that in a pipeline like this. What you have to do is have multiple bind groups and set multiple buffers when you're doing your drawing. I have a demo for this coming up in a future lecture to demonstrate this, but for now we're just doing quite a simple one here. So that is all of our setup there. So when we render now, again we're going to create a texture. This texture is our render attachment, the thing we're going to render into. We are going to create a texture view, and from that we are going to add in a few other bits and pieces. So what we're going to do is we're going to add in our command encoder. So we're going to create our command encoder, we're going to generate our render pass, we're going to render to the view texture view, we are going to clear on load, we're going to store on write, there's our background color. Then update uniform buffer. It's a function that's going to be called every frame, but basically what it does is it calculates the rotation. It's going to generate this MVP matrix by multiplying project by view by rotation, and then we get that data, flatten it into flat 16 floats, and then we set that into the uniform, and then that gets written to the uniform buffer that we generated. So basically this is how we pass that data to the GPU to be used in shader. So we set that uniform buffer, then we set the viewport, set our render pipeline, set the bind groups. Again, at the moment these values we're not going to go into, so these are just sort of default arbitrary values. Later on this becomes important when we want to set multiple buffers and things like that. We're setting our vertex buffer, we're drawing the number of points, we're entering our render pass, then we enqueue this to be rendered and update the color buffer. Again, the updating of the color buffer is exactly the same as before. We need to create a readback buffer. We then need to go through, create a render queue to copy that back from the GPU to our side, which then gets submitted. We synchronize that read back so that we can read the data back into our NumPy frame buffer, and then that gets sent directly to the widget for rendering. That is about it now, I think, for this demo. So you can see it's far more complex than the OpenGL demo, but we get a lot more out of it when we start doing sort of bigger points and things like that. And it's basically the fundamental processes now of how WebGPU works.